Hi, everyone. My name is Sebastian Muriel, and I'm the application engineer for protection devices. And today we're going to be going over TI's ESD protection devices and new dedicated solutions for Canon. So moving on to the agenda, I'm going to give a brief introduction to ESD protection and what ESD is and where ESD protection is used, along with the key parameters of ESD protection devices and their impact on system performance. And then I'll briefly go over how to choose an ESD device for any application. After that, we'll do a little intro to controller area network CAN and local interconnect network LIN. And then I'll give a device family overview of our ESD protection solutions for CAN and LIN and industry standard packages. So, what is electrostatic discharge and where is ESD protection used? So, electrostatic discharge is the sudden release of stored static electricity, and the release of electricity goes from one charged object to another. This charge can be transferred through the direct contact, which is referred to as contact discharge, or through the air, which is referred to as air gap discharge. And many of you may have experienced ESD by touching a metal object such as a doorknob or a car door. And while these strikes aren't harmful to humans, the voltages produced are in the thousands of volts and they can harm sensitive integrated circuits. And as ICs continue to decrease in size due to process innovations, they become more susceptible to ESD voltages. And as you can see here in the bottom left, there's a list of ESD events and the relative voltages that they produce at 20% relative humidity. And just a quick note that ESD voltage will typically be lower in higher humidity environments due to the resistance to the air increasing. So where do we place ESD protection? Well, ESD suppressors are typically placed in parallel between the source of ESD, which is typically an exposed interface connector, and the IC that needs protection. That during an ESD strike, the high voltage will cause the diode to break down, and it will provide a low impedance path to redirect the current to ground, as you can see with the ESD strike with protection image here. And the voltage waveforms are shown here on the right with and without an ESD diode. And you can see the blue waveform with the ESD diode. This is the voltage that the protected IC is going to see. So where is ESD protection used? So ESD protection devices are used in almost any application, and the main entry point for ESD across most of the applications here are exposed interface connectors. So these are just some examples of common interfaces that need protection across these, and a way to break out our portfolio and different interfaces that we protect. But you will see interfaces such as USB or Ethernet across many of these applications. So here you can get an idea of all the different devices that we offer for many popular interfaces across lots of different applications. And we have voltages from 3.6 volts all the way to 36 volt and looking to expand to higher voltages as well. And we'll have diodes to meet your needs with different specs that we'll cover going on. So let's go over the key parameters of ESD protection devices and their impact on system performance. So the first key parameter I want to talk about is working voltage. And working voltage, or VRWM, is defined as the maximum positive and negative voltage where current flowing through the diode does not exceed a certain amperage, typically in the low nanoamp range. So this is the IV curve for a 3.6 volt diode here. You can see that the working voltage is taking at a leakage of no more than 10 nanoamps. And the main point here is that the working voltage should encompass the entire interface's voltage range to minimize leakage during operation. If you use this 3.6 volt diode on a 5 volt line, you would be leaking a lot more current during operation. And so once the voltage exceeds the working voltage, it approaches the breakdown voltage, which is defined as the voltage where current through the diode exceeds 1 milliamp. And this is true for most of our lower voltage devices. Some of our higher voltage devices will be spec'd at 10 milliamps. And it's important to keep in mind polarity when we're talking about working voltage. So as you can see here, the polarity is going to influence the working voltage of the device. And we offer two polarities, bidirectional and unidirectional devices. As you can see, the bidirectional devices break down in the positive and negative region. And these are typically used to protect signals that swing below ground. And they're also commonly used to protect from miswiring events. And you can see the unidirectional IV curve here on the right. It breaks down in the positive region and then breaks down much earlier in the negative region, almost immediately. And so this unidirectional configuration can only protect positive interface voltage ranges. And if a bidirectional device isn't needed to encompass your interface voltage range, you can use a unidirectional device, and it's going to offer better protection in the negative region due to the lower negative breakdown voltage. So negative ESD strikes, you'll get better protection with the unidirectional device. So sorry for the technical difficulty there, guys. So let's get back on track. Talking about the key parameters for ESD diodes, capacitance. So for the capacitance of the diode must be low enough to not degrade the signal integrity of the protected line. And this is more of a care about for high-speed signals. Slower speed data lines and power lines won't require low capacitance diodes. And capacitance requirements will vary from system to system. Thus, capacitance recommendations are broad. And TI's low capacitance diodes are going to typically offer an insertion loss graph in the data sheet, which you can reference to see what signal speeds the diode can support and the insertion loss at those frequencies. The general rule of thumb is to protect signals with speeds up to the -3 dB point. And it's important to note that diodes with a lower capacitance will cause less insertion loss at higher frequencies. And moving on to more careabouts of capacitance for high-speed signals, interfaces such as USB and HDMI are going to require meeting compliance for the interface standards. So eye diagrams are commonly used to evaluate the signal quality of high-speed signals. And you can see on the left here a compliant eye diagram for USB 3.1, and on the right a non-compliant USB 3.1 eye diagram. And this is going to be due to increased trace capacitance, which will increase signal rise and fall times and shut the eye. And TI's low capacitance diode data sheets are going to offer eye diagrams for common interfaces supported. So moving on to ESD standards. Many of you might be familiar with HBM and CDM standards and IC data sheets. The CDM simulates an integrated circuit charging and discharging, and the HBM simulates a human being discharging onto the IC in a controlled ESD environment. These standards are useful in ensuring that components will survive manufacturing and assembly in factories where there's protocols to minimize ESD exposure. However, they don't accurately model real world. Accurately model ESD strikes, the International Electrotechnical Commission, IEC, created a more rigorous standard called IEC 61000-4-2. And this pulse will have a much higher peak and a faster rise time, as well as a longer pulse duration than HBM and CDM, which will be much more strenuous. And moving on to ISO and IEC ratings, ISO is just going to be a automotive standard, very similar to IEC, and the main difference is that the coupling networks in the ESD gun are going to be different. And now going over surge versus ESD. My main point here is just that surge pulses are going to contain significantly more energy than an ESD pulse, and this is due to the much longer pulse width of the surge pulse. The ESD will have a higher peak, but it will only have a duration of about 100 nanoseconds, while surge will last about 20 microseconds. So moving on to how to choose an ESD device for any application. Here's kind of a summary of the specs that we've gone over. For working voltage, you're going to want that max voltage of the protected signal. For choosing the polarity, you'll want bidirectional for differential signals, AC signals, or protecting from DC miswiring events. Otherwise, if you have a positive voltage interface, then it's a unidirectional. And for clamping voltage, you're going to want to find the ABS max ratings of the IC you're trying to protect and try to meet that ABS max rating with the clamping voltage. And for capacitance, you're going to want to look at that signal speed and determine what capacitance you're going to need to stay in compliance. And for your IEC ESD surge ratings, these will depend on your environment and handling. And we offer devices from 30 kV all the way down to 8 kV, as well as surge ratings from 2.5 amps to over 40 amps. So now we're going to give a quick intro to controller area network CAN and local interconnect network LIN. So CAN and LIN in automotive applications are CAN is typically a 2-wire differential communications interface, which has its physical layer defined by the ISO 11898-2 standard. And LIN is going to be typically implemented as a sub-bus of CAN. And these two interfaces are very popular in the automotive industry and are used for a variety of applications, including advanced driver assistance systems, body electronics and lighting, and powertrain systems. And LIN is going to be typically used for non-safety critical functions. And so going over CAN and LIN protocol data rates, the CAN protocol has evolved over time. Low-speed CAN offering data rates of 125 kilobits per second, up to the latest CAN XL offering up to 10 to 20 megabits per second. And the LIN protocol is going to be limited to 20 kilobits per second. So our ESD solutions here are going to have enough low capacitance to support signal speeds of about 1 gigabit per second. So they can support any CAN protocol or LIN protocol. And moving on to the signal voltages of these interfaces, the CAN data lines are low voltage. However, in vehicles, there is a common mode voltage present on the bus that is dependent on the battery voltage. This will require a diode with a higher working voltage to avoid the diode breaking down during normal operation. And the LIN data lines are going to range from 9 to 18 volt. But again, there's a common mode voltage present on the bus due to battery voltage. And this is, again, going to require a diode with a higher working voltage. And for your clamping voltage specs, you're going to want to look at that CAN and LIN transceiver you're using. For TI, the pin ratings for CAN H and CAN L transceivers are going to range from 14 volts all the way to 70 volts. And for LIN, these are going to vary from 40 volts to 60 volts. So here's kind of a summary of the CAN and LIN interface requirements that we've been talking about. And just note here, the clamping and capacitance, this is a general recommendation. Again, always take a look at the CAN and LIN transceiver you're using. And for capacitance, just a general recommendation, you could probably get away with a little bit higher capacitance. But all our ESD solutions are going to be much lower capacitance here. So designers will have plenty of extra room in their capacitance budget. So moving on to ESD to CAN overview. So ESD to CAN is a 2-channel device with a 24-volt working voltage. And this part was basically designed for CAN lines and 12-volt battery systems to prevent damage from improper jump starts or DC faults. And this device is offered in industry standard packages, SOT23 and SC70, making it pin-to-pin compatible with most competitor solutions. And the IEC and ISO ratings are going to offer the highest level protection at 30 kV. And again, the low line capacitance of ESD to CAN 24 at 3 puff is going to be able to support any of the CAN protocols, leaving room for designing in the future. If CAN ever comes out with a faster data rate, you'll have some breathing room with the capacitance with our diode solution. And here you can see an oscilloscope shot of CAN H, CAN L line communication with and without an ESD diode. And this is going to be for high-speed CAN with a data rate of 1 megabit per second. And as you can see, the waveform with ESD to CAN shows very minimal attenuation with the diode on there, so there's no concerns with signal integrity. Now moving on to LIN. It's very similar to CAN, but it is a one-channel 24-volt device in a SOD 323 package, which is an industry standard, so this will allow for some layout flexibility. It's going to be a low clamping device, about 40 volts for an 8 kV ESD strike, which should protect virtually any of TI's CAN transceiver or LIN transceivers. And the IC and ISO ESD ratings are maxed out at 30 kV. And again, the low line capacitance here of 2.3 puff is more than sufficient for LIN data rates, leaving the designer a lot more room in their capacitance budget. So moving on to the CAN and LIN ESD families. Here's the overall summary of these families. And the main spec to compare between these devices is the ESD rating. The lower capacitance variants of the 1 and 2 channel devices have lower ESD ratings, so they're going to be offered at a lower cost, and consequently the lower cap options are going to have lower surge current ratings and slightly higher clamping voltage. And as discussed previously, the IEC 61000 rating is going to be dependent on the handling of the end equipment and the environment, and basically ESD can happen to any system with exposed connectors, including CAN and LIN bus interfaces. So typically these connectors are exposed during vehicle assembly maintenance. For example, when a car is going through assembly, the cabling needed to connect to the control modules in the car can accumulate an excess amount of charge on them as they move through the factory. When it comes time to connect these cables to the control modules that hold the CAN and LIN transceivers, the excess charge will flow from the cable module and into the transceiver. And depending on the environmental conditions in the factory and how the cabling is handled, these discharges can get up to 30 kV and permanently cause damage. And this could also happen if a mechanic is performing maintenance on a car and has to disconnect and reconnect this cable. So in summary, anytime the cabling is manipulated in the system, there's going to be a chance for ESD. And all of these devices are going to be pin-to-pin compatible with multiple competitor CAN and LIN ESD diodes, and the line capacitance of our devices are going to be much lower than most competitor solutions out there, leaving designers a little more room in their capacitance budget. And clamping voltages were chosen to protect the majority of TI's CAN and LIN transceivers. And it's important to note that there is a little bit of use of CAN and LIN outside of automotive application, and we offer commercial variants of these devices with the same specs and packages. And similar to CAN, like these diodes could be used to protect the lower voltage line and can provide overvoltage protection for 24 volts. So we mainly discussed ESD protection in this presentation, but I would like to mention that our portfolio also offers data line surge protection diodes with up to 40 amps of protection for the IEC 61000-4-5 standard. And it's important to note that ESD diodes are going to offer some level of IEC surge protection, and surge protection diodes will offer a level of IEC ESD protection. And so here you can get a glance of our full portfolio, automotive offerings and commercial offerings. And we have key features here, such as small size, multi-channel, ultra low capacitance. And we're going to have key features here for pretty much all our voltage nodes from 3.6 or 5.5 volt all the way to 36 volts. And we are looking on expanding. And so here is some resources for you guys to reference. Here the ED forum, we're under interface, and you can post a question here asking anything about ESD diodes, and I'll be able to answer that. And here's a link to the ESD fundamentals. This can go into the specs a little deeper if you have any questions there. The system level ESD guide will give you a good idea of where ESD is used and how to choose an ESD diode for a lot of our common applications. And down here is a link to one of our ESD EVMs. And this is going to support most of our single and multi-channel packages, so you can do your own ESD testing. And I wanted to address a question in the chat from Richard. So he asked, using CAN on a 24-volt vehicle, we have seen voltages approaching 40 volts. If there are components that will work in this environment, again, we're going to be coming out with an ESD CAN 48, which will address this use case. So if there's any more questions, I can go ahead and answer that now. We're at the end of the presentation.
All right, thank you, Sebastian. And we apologize to everyone for the technical difficulties during today's session, but appreciate you hanging in there while we work through them. We had pinpointed what the issue was, so next week should be a much smoother experience for everyone. Thank you for joining today's MPU webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. So don't forget to visit ti.com/MPU to register for next week's topic, industry's first active EMI filter, ICs with reduced filter, size, weight, and cost. On ti.com/MPU, you can also view upcoming topics for out to the next 4 weeks, as well as viewing all past recordings on demand. Thank you again for everyone joining. Apologize again for the technical difficulties, and see you next week. Oh, and real quick, I just saw Richard's question, will the slides be available? Yes, so they are available to download. If you go to ti.com/MPU, the recording will be available next week. From there, you can download the slides and any additional content. All right, thanks again, everyone, and hope you have a great rest of the day, and see you next week.
Thank you, everyone.